Welcome to this session. Today's topic of the discussion is the PN junction diode and rectifiers. My name is Ajit Subhash Surinshi. I am from the Electronics and Telecommunication Department from Walchand Institute of Technology, Solapur. So, objective learning outcome of this session is that at the end of the session, student will able to explain the working of the PN junction diode and one application, that is as a rectifier, half-wave rectifier. So content in this session is what is the prerequisite. Prerequisite is the previous knowledge you required for PN junction diode, junction formation and equilibrium, depletion layer and potential barrier, symbol and conventional currents, external bias, VI characteristics, current equations and equivalent circuits of the diode, and diode as a half-wave rectifier, and different parameters of the half-wave rectifiers. So prerequisite, before proceeding further into this session, should have a knowledge of the basic semiconductors. What is this mean by the semiconductors? So junction formation and equilibrium. So in the junction formation, so all of you are aware about the p-type semiconductor is when acceptor impurities or trivalent impurities is added with the silicon or germanium pure intrinsic semiconductor. It forms a p-type semiconductors. So trivalent impurities acquires a negative charge on it, and in the silicon and germanium, when impurities of the donor impurity or n-type impurity is added, so it is get ionized to form a one excess of electron, and it acquires the positive charge on it. So by forming a junction, there are various techniques of forming the junction here. So one of the technique is the diffusion technique and etching techniques. So by diffusion techniques, what happens when PN and junction is formed? So some of the electrons, some of the holes from the P side region will cross to the N region, and it will combine with the electrons, and electrons from the N region will cross into P region. It forms a recombination and it left the immobile charges. So there are two charges, immobile charges. Immobile charges are basically the impurity atoms there. As you can see here, this is the negative charge. So these are immobile charges. These are the immobile charges, and these are the mobile charges. So it forming a depletion region. Depletion region is the depletion of the mobile charges in this region. And it forms a equilibrium in the sense that when the negative charge from the P side and the positive charge from the N side becomes equal, a further flow of the electrons, mobility carriers, that is holes from the P sides, and the electrons from the N side will halt. Okay, so this condition is called as a equilibrium condition. So forming the PN junction diode. So this is without an external bias or external voltage. So depletion layer and the potential barrier. So depletion layer is the absence of an electron mobility at the center of this junction. So this is the negative charged electrons, and these are the positively charged negatively charged immobile ions and positively charged immobile ions, and forming this depletion region, and it will obstruct the further flow of the electron from the N side and hole from the P side. And this is the potential barrier. So this barrier is for the holes crossing from the P side to the N side. And there is one more type of the barrier which obstruct the flow of the electron from N side to crossing to the P side. So this is a depletion region and the potential barrier. So at the equilibrium, the potential barrier width or potential barrier height of the for the holes and the potential barrier height for the electrons will nearly equal. So what is the symbols and the conventional direction current, conventional direction of the current in the diode? So this is a p-type, n-type forming the PN junction, and these are the metal contacts. So P type, it is normally identified with when external lead is metal lead is identified as anode, and external metal lead connected to the N side, it is identified as a cathode. So this is forming the anode and cathode. So this direction itself is giving the direction of the conventional current. So conventional current is from the positive terminal to the negative terminal of the battery. So from the positive charges to the negative charges. So what happens when you apply the external bias? External bias means it is applying the external voltage to the PN junction diode. So when we apply the voltage in such a direction that positive battery positive is positive, it is connected to the P type, and battery negative is connected to the N type. So it is forming the forward biased PN junction. So in the forward biased PN junction, what happens? The depletion region is reduces, because it is forcing the electron from N side to cross the PN junction diode, and it is forcing the electron holes from the P side to cross the junction PN junction diode. So large amount of the current starts flowing in the forward bias for PN junction diode. And what happens in the reverse bias when N type of the semiconductor is connected to the positive terminal of the battery, and negative terminal of the battery is connected to the P side? So it increases further the depletion region, and it makes it impossible to the flow of the current through the PN junction diode. So very small or negligible amount of the current flows when the diode is reverse biased by using a battery in such a polarity. So this is the conduction in a PN junction diode. So VI characteristics of the diode. So this is VI characteristics. To measure a current through a diode, ammeter is used, and to measure a voltage across diode, a voltmeter is used, and there is one current limiting resistor is placed here, and this is a variable voltage source. So this variable voltage source changing the voltage from the 0 to the positive, 0 to the negative. Okay, so when voltage source is a positive, that is positive is connected to the positive of the diode, and negative is connected to the negative of the diode, negative terminal of the diode, that is cathode terminal of the diode. So diode is get forward bias, and during forward bias, as you can observe, up to the knee voltage or knee point, a current is very small, a very negligible amount of the current flows through the diode, and after knee point, a diode start conducting heavily. So this is for following the path which is the exponential path, and after that it is a large amount of the current flows through the diode. And in the reverse bias, you can connect a battery in the opposite polarity, or you can reverse the polarity of the diode here. So once you reverse the battery polarity, diode is get reverse biased, and in the reverse bias, a very small amount of the current, and in range of the microampere flows through the diode. So this current is called as a reverse saturation current, and at the sufficiently higher reverse voltage of the battery, this voltage is very high as compared to the knee voltage. So that voltage is called as avalanche breakdown, and in that avalanche breakdown, the diode is get burned, and a large amount of the current starts flowing through the diode. So this is about the VI characteristics. So current equation and the resistance. So in the diode equation, current equation can be given by ID is equal to, here I0 is the reverse saturation current, and VD is the voltage across diode, and neta is the ideality factor. So ideality factor for the silicon is 2, and for germanium it is 1. So VT is the temperature equivalent voltage, and it is given by the KT. So K is the Boltzmann constant, it is 1 upon 11,600 electron volt degree Kelvin. So this equation this equation is actually the model of this this VI characteristics. So diode static resistance is given by so when you divide the voltage during the forward bias, when you divide the voltage with current, it is called as a diode static resistance. It is also called as a DC resistance. DC resistance is very small for a diode, because as you can see, this graph is almost vertical. So this vertical graph, that means resistance is very small during the forward bias of the diode. And diode dynamic resistance, or it is called as AC resistance, rate of change of the voltage with respect to the current in the diode is called as a diode AC dynamic resistance or AC resistance. What happens when you apply the AC to the diode? So it present the AC resistance, and it is also called as a dynamic resistance. So when you differentiate this equation VD with respect to ID, you will get such kind of the equation, neta VT divided by ID plus I0. So this is a diode resistance. And what is meant by the equivalent circuit? So in the equivalent circuit of the diode, if you replace the diode in the forward bias, so this can be replaced with the forward resistance and the threshold voltage, or it is also called as a knee voltage. And this is actual model of the diode for forward bias condition. So where RF is the forward resistance of the diode. And if you neglect the forward resistance, which is very small, to a 0, and if you neglect the knee voltage, which is for 0.7 for the silicon diode and around 0.3 for the germanium diode, so after neglecting this, we can replace this diode as a closed circuits. So this is about the equivalent circuits. And diode as a half-wave rectifier. So in the half-wave rectifier, diode have a, as you can see, this is a positive half cycles. When you apply AC to the diode in both direction, it is get positive half cycles. So these are the different parameters of the half-wave rectifier. So DC current of DC voltage, and efficiency of the half-wave rectifier is around 40.6. So this is one of the application of the diode as a half-wave rectifier. So these are some references. Thank you.